Okay, we are time traveling again. We're going back in time to section 3.1. So it's a little awkward because we've gotten as far as, the middle of the chapter in 3.3, and now we're going backwards. So what our focus is today is on global extrema. Okay, that means the highest of the highs and the lowest of the lows. Okay, so this is referring to the absolute max, the highest of the highs, and the absolute min of the function. Okay, sometimes we call it the global max and the global min. Sometimes we just call it the maximum, like the Ohio State University, right? We kind of just classify the phrase max to mean the global kind. And then, of course, likewise for the word the minimum, just means the lowest point. So I want you to take a minute and look at these two graphs given to you here. These are actually from the function y equals 4 minus x squared. And then I want you to fill in the highest point, the lowest point, highest point, and lowest point here. Okay. So when we come back, what we should find is that the maximum for the first one is 4, and the minimum value is 0. Remember, we report highs and lows as maxes and mins, right? In the second one, we have a maximum still of 4, but the minimum, right, does not exist because we're trending over here towards 0, but we never really get there due to that open circle, right? So there's technically no minimum there whatsoever. And what this causes us to want, right, us little mathematicians, is that we want to know, well, when will I for sure have a max and when will I know if I have a min? Okay, and here's how you know that, okay, is the extreme value theorem, affectionately referred to as EVT. This goes along with MVT and IVT and all the other VTs that you've been learning this year. So the extreme value theorem is pretty simple. It just says if f of x is continuous on a closed interval, okay, brackets, not parentheses, then f of x has one max and one minimum. Okay, so there's nothing about differentiability. It just has to do with the continuity and the closure of the interval itself. So you'll notice the first example did have a closed interval, right? Because the endpoints were closed at -2 and at 1 at those x values. The second one, of course, had an open interval. And that's why we don't necessarily have a minimum existing, because the intervals were open, and that kind of changes things up. So we are going to embark upon an algebraic path to finding these extrema. Okay. I want you to take a moment and answer the question about what test have we learned for finding relative extrema? Okay, and what's that process like? Okay, so when we find relative extrema, we use the first derivative test. We create a sign chart. We look for the derivative to be changing from minus to plus or vice versa. Okay, finding global extrema is a little bit different. Whoa, let's not do that. Finding global extrema, right, has us finding critical numbers. So that's the same step, number 1. Number 2 here says maybe make a sign chart. So there's times when this is going to be important and times when it's not going to be important. So we'll kind of look through examples as we go on there. And then number 3 says to evaluate the appropriate critical numbers and endpoints in the original function. So this phrase appropriate, right, is what the sign chart might be helpful for. Not every critical number is going to necessarily yield the max or min. The sign chart helps us decide that. And then the brand new aspect, right, is that we not only can find extrema at critical numbers, but they also might occur at endpoints. And that's very different from relative extrema. And then step 4 is just once we plug in and do the evaluation from step 3, we pick the highest number to call it the maximum and the lowest number to call it the minimum. So let's try example 1 here. It says find the extrema of f of x. plus sine x over 0 to 2 pi. So 0 and 2 pi, those are the endpoints that we're talking about in that highlighted step up there in number 3. So we're going to start by doing the critical numbers. So I'm going to take the derivative. I'm going to get 1 plus cosine x for my derivative. I'm going to set that equal to 0. I'm going to subtract 1 from both sides. And then I'm going to think about the cosine function and where it is -1. The only value, right, I can think of is pi. Okay, so pi is the only critical number within that interval. Okay, so step 1, check. Number 2, maybe make a sign chart. Okay, we might do that later, but since it says we can skip that step, I'm going to actually take us to step 3 here and evaluate the critical numbers and the endpoints in the function. Okay, so skipping step 2, I am going to plug 0, the endpoint. I'm going to plug in the critical number of pi, and then I'm going to plug in the other endpoint. Okay, so remember that these two guys here on the outside are endpoint values, and those are sneaky places where the maximum or minimum might occur. Okay, and then this guy here in the middle is the critical number. So now we're going to plug those in to the original f function, right? So I'm doing 0 plus sine of 0. Very awkwardly ends up also being 0. F of pi itself is pi plus sine of pi. Since sine of pi is 0, we're getting pi plus 0, so it's pi. And then when I do 2 pi, I've got 2 pi plus sine of 2 pi, which that part is 0, so it's 2 pi plus 0, so it's 2 pi. So this evaluation is enough to tell me that the maximum is 2 pi. Because of these 3 y values, 2 pi is the highest, and then the minimum value is 0. Okay, so that's the highest and the lowest there. I guess real quick, I might just throw down a sign chart here to show what it looks like. If I cap this at 0 and 2 pi, and I plug test points in and around, like if I use pi halves and 3 pi halves, here and here, the derivative is positive, right? So what that means, right, this sign chart tells me that f is increasing the whole time, right? And that means if it's going up and up and up, it means the first value was at 0, right, was going to be the low point, and that the value at 2 pi, whatever that is going to be the high point. And this step where I actually plugged in pi was not necessary because it's not really even going to yield a maximum of any sort. So this is a pretty cool function. It kind of just curves. It's pretty curvy, and it just kind of like continues increasing and getting flat, increasing and getting flat as time goes on, or as x values get larger and larger. So it's a neat one to check out. But that's just why the sign chart might save us a little bit of work, because then I wouldn't have had to evaluate it pi. Let's go down to number 2. It's just a little polynomial function. So let's go ahead and find the critical numbers. Derivative is 12x cubed minus 12x squared. I'm going to set that equal to 0. I'm going to factor like a boss. Remember when that was cool to say? This factor gives me x equals 0 as a critical number. This factor gives me 1. I don't need to do a sign chart for this one. But I do have to do step 3, where I go ahead and evaluate f of -1, first endpoint. Actually, let me kind of color coordinate this a little bit better. F of 0, my first critical number, and then f of 1, my second critical number, and then back to my blue endpoint. Okay, so f of -1 is 3 times -1 to the 4th minus 4 times -1 cubed, which is 3 times +1 minus 4 times -1. So that would be 3 plus 4, giving me 7. f of 0 is 0, just as a quick glance of plugging in 0. F of 1 is 3 minus 4, which is negative 1. And f of 2, ooh, this is going to be fun, a little bit of math here, gives me, let's see, 2 to the 4th power is 16 times 3. So I've got 48 for my first term, and my second term is 8 times 4, which is 32. 48 minus 32 is 16. So now remember, this step here is where I compare the calculations of the y values, and whichever y value is the highest, that's my max, and whichever one is the lowest is my min. So my maximum is 16, and my minimum is -1. The end. All right. I think, let's see what comes of the next one. I think the next one might be a really good one for you to try on your own right now and see. Okay, again, the idea here, do your critical numbers. Okay, and then do your evaluations. That's, kind of the step 3 that we're talking about. Okay, making sure to include the endpoint evaluations. And again, this is done without a calculator. So try to grind through this without a calculator. It will serve you best in the long run. Okay. All right, so the derivative that you should have got here in number 1 ends up being, actually I'm probably, f prime, the simplified version of f prime is 1 minus x over 1 plus x, just to help you get critical numbers, and then the denominator is x squared plus 1 squared. Okay, that gives us critical numbers of positive and -1, and then the denominator has no critical numbers because that's never going to be equal to 0. Okay, and then the values that you should have plugged in here, we get -3/10 for that one. Remember, we're going back to the original. F of -1 gives you -1/2. F of +1 gives you +1/2. And f of 2, going back to the original again, gives you 2/5. And if you're not so great at decimals, right, you might want to, or as fractions, you might want to write them as decimals to help you figure out highest and lowest. Maximum here, minimum here. Okay. All right. What do we have going on here? All right, number 3 has us working a little bit with the e to the x function. So I want to take you through that one because we have not done that a ton together. So let's start by the critical numbers. Let's think about what rule I have to use to take this derivative. Got to be the product rule. So f prime is first times the derivative of the second plus the second times the derivative of the first. And then in order to set that equal to 0, again, it's going to help me to take the GCF, right, out of both terms, right? I'm thinking of this as one term and this is a second term. So I'm going to factor out an x e to the x and then be left with x plus 2. And that's what I'm setting equal to 0. So now I've got x equal to 0, I've got e to the x equal to 0, and then I've got x plus 2 equal to 0. One critical number here. This equation has no solution because e to the x, just that standard parent function, is always positive. And then it gives me -2 over here. And then step 3 here is to go ahead and evaluate all these. So let's use the endpoints. Let's go to criticals. Oh, kind of not in the right order, but that's cool. Order really doesn't matter there. And then the other endpoint. And let's make these calculations. So I've got -3 squared times e to the -3, which is 9 over e cubed if I simplify it. e to the 0 is 0 squared times e to the 0, which is 0 times 1. That's 0. If I plug in -2, I get -2 squared times e to the -2, which simplifies to 4 in the numerator, e squared in the denominator, and then f of 1 is 1 squared times e to the 1, which is e. And then I have to try to figure out the max and the min, right? So the maximum value, if you look at these 4 numbers, right, which one of them is the highest? Out of this guy, this guy, this guy, this guy. My hint to you is that it might be helpful to know e is roughly 2.718. It's irrational, so it's non-repeating and goes on forever, like pi. And so think about which of these might be the max and which of these might be the min. So the maximum should be e. That's the highest of all the numbers. We are for sure that these numbers are somewhere between 0 and 1 in value, right? Because they're just fractions. Okay, so that means because they are between 0 and 1, that 0 must be the minimum. And that would be your final answer there. We are going to save a calculator talk here in example 5 for class. So that kind of concludes this notes section. You can give example 5 a try if you want to think through it. My hint to you is to graph this function, change your window to look just between 0 and 2, and then use zoom trig to see what it looks like, and then see if you can make a good guess. I'll leave a question here at the end for you to plug in what you get and see if you are right or wrong.